Hello everyone, and welcome back to our series on quantum mechanics. In the last video, we derived the energy levels and eigenstates of the quantum harmonic oscillator, or QHO, using ladder operators. In this video, we will derive the QHO, eigenstates, and energy levels in an alternative fashion using analytic differential equation solving techniques. You may be wondering why we are bothering at all with this alternative approach. After all, why go about solving a problem that we have already solved before? Well, both of these methods are useful to know since they are often applicable for other problems in different circumstances. In particular, whenever a Hamiltonian can be factored nicely, we can use the algebraic approach to write our Hamiltonian in a quadratic form. On the other hand, if we have knowledge about the asymptotic behavior of our energy eigenstates, we can instead opt to use the analytic method we describe in this video. As you may recall from the last lecture, the potential for the QHO is given as follows. Substituting this into the time-independent Schrödinger equation, we get the following differential equation. To make our lives easier, let's reparameterize our Hamiltonian in terms of psi equals the square root of m omega over h bar times x, and k equals 2e over h bar omega. We can then rearrange this differential equation into the following form. Let us now consider what happens asymptotically when x, or in other words, psi, is large. In particular, suppose psi is significantly larger than this energy term k. We then approximately have the following ODE. Solving this in the asymptotic limit, we essentially need solutions where taking the derivative twice gives us a multiplicative factor that is asymptotically equal to psi squared. This can be accomplished by picking a function whose derivative produces a multiplicative factor of plus or minus psi, in other words, exponentials of quadratics. We can verify this by taking the second derivative and showing that the psi squared term dominates the rest of the polynomial multiplied by the exponential. Hence, we choose a solution that is a linear combination of these two expressions. Since the wave function must vanish as x or psi goes to infinity for the state to be normalizable, we can eliminate the term with plus psi squared over 2. Since the true solution is likely not just a Gaussian, we can replace this constant a with a function u to get complete equality, giving us the following ansatz for our solution. If we then substitute this expression for the solution into the ODE and simplify, we get the following ODE, which is known as a Hermite differential equation, whose solutions, as you might expect based on the name, take the form of Hermite polynomials. To show this, we use the power series method, where we set u equal to some power series and then solve for the coefficients as follows. For the differential equation to equal 0 for all psi, we must have both the left term outside the series equal to 0 and the series coefficients all equal to 0, giving us the following two relations. Since the relation on the left is simply a special case of the one on the right that occurs when j equals 0, we can combine these relations as follows by changing j to start from 0 rather than 1, meaning that we have the following recurrence relation for all the coefficients. Since each coefficient for psi to the j is proportional to the coefficient of the term with psi to the j minus 2 and vice versa, we have that we can split our solution into the sum of an even series scaled by a0 and an odd power series scaled by a1. However, we run into a problem. It seems as though for arbitrary k, these series could go on infinitely, and the growth of u of psi could be too fast. In particular, consider the asymptotic limit of terms, where j goes to infinity. We can see that the recurrence relation asymptotically reduces to the following, which actually turns out to be proportional to the power series for the exponential of a quadratic. Hence, we have that if we allow infinite terms, u of psi will grow as fast as the exponential of psi squared, meaning that our solution will not be normalizable. Consequently, the only option is that the series must truncate. Hence, we have to choose k equal to 2 times n plus 1 for some integer n, fixing our energy levels as E equals h bar omega times n plus 1/2. As a result, we now get that u sub n of psi is a truncated polynomial of degree n, which is simply the nth Hermite polynomial as we defined it in the last episode. You can check this on your own time if you wish. Therefore, if we were to compute the additional normalization factor, we would find that the eigenstates are given in the following form, exactly as we saw last time. Consequently, asymptotic analysis gives us another powerful approach to computing energy levels and eigenstates for different potentials. In the previous video, I didn't say too much about the general shape of the eigenstates, as I was more focused on the actual derivations themselves. So, let's take the time to talk about this. Since the potential is an even function, we know from our symmetry properties that we should have even and odd eigenstates. In particular, we can see that eigenstates with odd n are odd, and those with even n are even. Furthermore, each eigenstate gains one more node as we go up in energy, with the ground state having 0 nodes, the first excited state having 1 node, etc. Let's plot the first few eigenstates over the potential to see how they look. Here, the dashed lines correspond to the energy level of the eigenstates relative to the potential, which is shown in blue. Treat each dashed line as a 0 line for each corresponding eigenstate I plotted. As you can see, the wave function has oscillatory behavior when v of x is less than e, and then rapidly decays outside this range just as a Gaussian does. This, however, means that unlike in the classical description of the harmonic oscillator, we have non-zero amplitude outside the classically allowed region where v of x is less than or equal to e. The classical turning points, which occur when the total energy E equals V, are represented by the points where these dashed lines intersect with the potential, as these are the points where the kinetic energy should be 0. So, how do we reconcile this inconsistency? Well, if we look at the solutions for higher energies, such as even, let's say, n equals 40, we can see that the probability of sampling something outside the classically allowed region drops off quite quickly. Note that here I plotted the actual probability distribution itself rather than the wave function for clarity's sake. Consequently, at the larger energy scales we observe in our everyday lives, it becomes ridiculously improbable to ever have the particle be located outside the classical region, and it would be basically imperceptible if it were even to happen. Let's compare this to the classical case. Firstly, how do we even define a classical probability distribution for the position of the oscillating particle? Well, suppose that I take a snapshot of the system at some time. The probability that the mass is at a given location in the range from x to x plus dx is given by rho of x times dx. This probability is also equal to the proportion of the time spent going from one end to the other that is spent going through this interval, which we define as dt over big T, which we can simplify as follows. Hence, we have the following expression for our density. Plotting this classical result versus our n equals 40 QHO solution, we can see that the classical distribution follows the average of the peaks and troughs that we observe in the quantum solution, meaning that as the energy level increases, in other words, as we tend to the classical limit, the classical solution serves as a better and better approximation of the equivalent quantum one. Altogether, this concludes our discussion on the quantum harmonic oscillator for now. In the next video, we will look at a new potential, the Dirac potential, in order to explore behavior about potentials that are spiked at a given point and give a preliminary introduction to scattering. I hope you enjoyed this video, and I will see you next time.